So before I start today's deliberations, let me just summarize what we discussed in the last class. We have mentioned system. System is basically a mapping from signal to signal. Okay, whereas signal is a mapping from a set of independent variables to a set of dependent variables. Whereas system is a mapping from a signal to signal. We call it mapping from the input signal to the output signal. And accordingly, what we have discussed, we have categorized the system into two classes. First one was on the basis of memory, whether the system encompasses a memory or not. So in that case, we can call the system as a memory-based system. If the system doesn't encompass any memory, we call it a memory-less system. On the other hand, if the system encompasses some memory, then we call it a memory-based system. Then after this one, then we have considered, or we have classified the systems in terms of stability. Most precisely, we have discussed about the bounded input, bounded output stability, VIVO stable system. That means if your system some bounded inputs for all possible bounded inputs, if a system produces bounded outputs, then we call the system as a VIVO stable system, or in other words, bounded input, bounded output stable system. So accordingly, we have classified the systems into two different categories based on the stability. One was the VIVO system, second one was VIVO unstable system, right? And we have given some examples for that. Then we consider the time invariance property of the system, right? So time invariance, so particularly this, in general, the property can be visualized as a shift invariance property, shift invariance, because as I mentioned that in this particular class we have observed the signal as a function of time, but remember that signal can be function of anything, right? So in general term, I can call a shift time invariant or shift invariant. So if we move from the 1D signal to the 2D signal, for example, image, then we don't call it a time invariant system, as a space invariant or space variant system, right? Depending upon the independent variables, because time doesn't carry any significance or importance. For image, the importance lies in the space, the coordinates, x coordinate, y coordinate, and accordingly we call it space invariant system. So to make it more general, we call it a shift invariant system. Shift invariant or shift variant. Right? So what is time invariant? So if we find that the system output, the system response doesn't depend on the time at which the input is applied, we call the system as a time invariant system. On the other hand, if the system depends explicitly on the time at which the input is applied, then we call the system as a time variant system. Right? So accordingly, based on this time invariance property, we have classified the system as time invariance or time invariant system, and we have given some examples for that. Now today, with this basic understanding, today we will move to the number fourth property, and this fourth property is known as the causality. Causality of this. So what do you mean by causality? So actually the term causality comes from the cause. Cause, you understand? Reason? So if the property of the system is the cause and effect relationship, right? If the response, or if I may call it like the property of the system, if the property follows or obeys the cause and effect relationship, then we call the system as a causal system. Okay, that means it must obey cause and effect relation. So if the system follows, or if the system obeys the cause and effect relation, then we call the system as a causal system. If not, then we call the system as a non-causal system. I am giving you an example. For example, say I some input something like that. Suppose this is t, x of t. Suppose this is the input variation, any arbitrary signal, t as a function of xt, and let's assume the signal is available only for t greater than 0. So xt basically 0 for t less than 0, right? Xt is equal to 0 for t less than 0, and for t greater than 0, xt is having some values. That is the signal we are talking about, and this is fed to a system. I don't know what type of system it is, but this is fed to a system. Now the system can produce actually three different types of outputs, but let's call two different types of outputs. Number one is this one. This output can be something like that. This is t. Let's call this is y1 of t, and the variation is something like that. Okay. Let's call this point. Let's call this point as, and let's call this point as t1, and say t1 is greater than or equal to t0. Okay, that means the input starts from t0. Input starts from t0 and output starts from t1. Now this t1 is greater than or equal to t0. That means first the input arrives and then the output right at this point or sometimes after that. That means first the cause is the signal x of t, that is the cause which is being in the system, that is the stimulus being provided to the system, right? And the response of the system is given by y1 of t, and that comes after the cause is present, either at time or after some data amount of time. So that's why t1 is either equal to t0 or t1 is greater than t0. That means so if this is the kind of relationship, then I can say that the output of the system y1t, it obeys the cause and effect relation, because you know that effect must arise after the cause is present. First you have the cause, and based on that some effect will be there. You don't expect that the effect will come before the cause is present. Right? Now had this been the case, then I call as a causal system. If not, that means I am having this kind of output. The second type of output, say let it be y2 of t. Y2 of t. This is t. This is y2 of t. And the variation is something like that. And this is quite obvious that if this point is t2, then t2 is obviously less than t0. Okay. Now, had this been the case, that means your output starts appearing even if the input is not present. It is quite obvious from the diagram itself that t0 is greater than 0 and this is the 0 axis, as you understand. T is equal to 0. And as you can see, the input appears after t equal to 0 and the output appears before t equal to 0. It's quite obvious that t2 is less than t0. So the output being produced by the system y2 of t is not due to the effect of the input on it. Right? So in that case, we call the system as a non-causal system. So either the system is a causal or the system is non-causal. So if the system owes a cause and effect relationship, then we call the system as a causal system. And for any practical system, that has a causal system. Because if you want to realize any system practically realizable, practically feasible system is always a causal system, because it must obey the cause and effect relation. If not, hypothetically I can assume, okay, there could have been some systems, but these are not physically realizable. Then these systems are known as the non-causal system. And there is a certain difference between the non-causal system and the anti-causal system. Okay, before discussing this, let me just give you some basic understanding behind the causal signal right. So causality is also applicable not only for the systems but also for the signal itself. So what do we mean a causal signal? So let us spend a few moments to understand causal signal. So a signal is said to be a causal. X of t is said to be causal if x of t is equal to 0 for all t less than 0. So here we consider that t is equal to 0 is the reference. T is equal to 0 is the reference. So if for all t less than 0, if the signal xt is equal to 0, then I call the system, I call the signal as a causal signal, right? So can you give me some example of a causal signal that you have already studied in this course? Any signal which is a causal signal. Unit step. Very good. So unit step ut. I can call unit step u of t is a causal signal because it exists for t greater or equal to 0. For t less than 0, this is always 0. It's a causal signal. Now, what is a non-causal signal? Causal signal is something which does not obey this formula. That means for xt, I mean, a signal is said to be non-causal. So when I call it causal signal, non-causal signal. So non-causal signal is something xt is non-causal if xt is not equal to 0 for t 0, for any t less than 0. If this condition doesn't hold good, I mean the first condition, then we call the system as a non-causal signal. Okay. Now this non-causality can be divided into different sections. One is purely non-causal, I call it non-causal. Then second one is, I mean this non-causal is a bigger set. So what does it mean? Xt is not exactly 0 for t less than. So for some value of t less than 0, you have some non-zero xt. But it doesn't say anything about t greater than 0. Nothing is mentioned because the causality, that the definition of causality is strictly on the variable or on the parameter t, on the condition t less than 0. So for t less than 0, x equal to 0, then we call the system, we call the signal as a causal signal. Now nothing is mentioned about t greater than 0. So with respect to t less than 0, I can classify the signal as a causal or non-causal signal. So for t less than 0, if x for all t less than 0, x equal to 0, we call the signal as a causal signal. If some t less than 0, if x is non-zero, then we call them, I mean if this condition, first condition is not satisfied, signal as a non-causal signal. Okay. Now nothing is mentioned about t greater than 0. Okay. Now you can have, so from this non-causality, non-causal is a set, superset, and within this superset you have a subset over there which we call anti-causal signal. Anti-causal. So non-causal and anti-causal, they are not the same. So what is anti-causal? It's just the reverse of causal. Can you get my point? Anti-causal basically which is not, I mean which does not follow the property of causality, or rather it follows the property of causality in a reverse way. That means a signal x of t is anti-causal if, now I should write xt is equal to 0 for t greater than 0. So if a signal is a causal, you understand what is meant by causal signal. If the signal is not causal, then it can be either, so I call it non-causal. If the signal is not causal, right? And within the bigger set of non-causality, I have a subset which is called anti-causal. That's the reverse of causal signal. So let me give you some example so you can understand. Let's take, you understand, okay, this is t, this is x of t, this is 1, this is 0. That's a simple causal signal, right? So using this u of t, this step function, I can make the signal. So this is a causal signal. Okay. So now let me write u of t so that you can understand it properly. U of t. Okay, this is a causal signal. Now tell me one signal operation. You just tell me a signal operation. Which operation? So this is a causal signal. This is a causal signal. Okay. I would like to make it say anti-causal. Reflection. Very good. So reflection is the operation. So if I reflect this is t. How does it look like? 1. This is anti-causal and signal. And what should I write over there? U of minus. Okay, that is anti-causal. Now the question is that, is it a non-causal signal? Is it non-causal? Yes. Yes. So, this anti-causal signal is a non-causal signal. All anti-causal signals, they are non-causal signals. So all anti-causal signals are non-causal, but not all the non-causal signals are anti-causal. This is anti-causal and this is non-causal. So you have the bigger set of non-causality, right? And within that you have a small subset which also obeys the anti-causality property. So that is the reflection. So can you tell me how can I make it non-causal? How can I make it non-causal? Or let's make it something like that. You have this one. You have this particular signal anti-causal. Okay. You have a signal, right? So I would like to make it. So anti-causal, as you know, it's a part of a non-causal. Part of, true sense, it doesn't obey the bigger perspective. So I would like to make it. It's not only anti-causal, but I'd like to make it non-causal. So how can I do that from anti-causal to non-causal? That means what? The anti-causal signal for t greater than 0. T greater than for anti-causal what? T greater than 0. This is always 0, right? Causal signal t less than 0, always 0. For all t, obviously. For all t, if you just go back to the causal signal t less than 0, for all t x equal to 0. Any doubt? Red chart. Any doubt? So t less than so causal signal means for all t less than equal to. Anti-causal just the opposite. For all t greater than 0, x is equal to 0. And what is non-causal? Non-causal is basically the mixture. It's a mixture. So I can't say for all t equal to 0 this is 0 or for all t greater than 0 this is 0. That means the non-causal will be there for t less than 0 as well as for t greater than 0. Right? So how can I make the signal non-causal? Strictly speaking, non-causal. How can I make it non-causal? Huh? No, from this anti-causal u of minus t. minus velocity constant. I mean u of minus t plus something like that. Is it? U of minus t minus t. No. The argument section, t section, or the intersignal section. Time. It's not called scaling. It's not scaling. Shifting. Yeah, shifting. So left shift or right shift? Right shift. Right? That means what? Yeah. So shifting is operation. Shifting is operation, and it will be something like that. The signal looks like this. Okay. This is any value, say t1. Any t1 which is greater than 0. Okay. Okay. So t1. So what signal u of what? U of minus t. Is it or plus? Is it minus t minus 1 or minus t plus t1? Is it minus t minus t1? How many in favor of this? U of minus t minus t1. Please, okay, it is minus t minus t1. Please raise your hands. Okay. And so, okay, how many are against this? Only 4 points. Okay. And can't say. Can't say. See, confused. How many of you are confused? These two numbers. So it's not equal to the exact class population. How to check that it is correct or not? How to check? How to check that this is correct or not? If I put, okay, he has told that. That's a very pertinent reply. So somebody is saying that, okay, u of minus t1, right? So, hey, note up. So if I put small t is equal to capital T1, small t is equal to capital T. Okay, yeah. Oh, it should be capital T1. Anyway, doesn't matter. This should be capital T1, right? So, if I put small t is equal to capital T1, you should expect that at u of 0 there is a discontinuity. At u of 0 there is a discontinuity. U0 minus is basically 0 and u0 plus is equal to 1. So there is a discontinuity at t is equal to 0. Okay. So now if we put t is equal to small t is equal to capital T1 over there, what do you get? And you know u of 0 minus is equal to 0 is equal to 1, and u of t is equal to 0 for all t less than 0, and that is 1 for all t greater than 0. That's the definition. So now if you put t is equal to T1 over there, what are you getting over there? U of minus to T1. And T1 is positive. So you have negative. That should be 0. Is it? No. Now if you put t, and if I make it like u of minus t plus T1, u of minus t plus T1, and if I put t is equal to T1, then that is u of 0, and u at u0 there is a discontinuity. From 0 to 1 there is a transition. So it is not u of minus t1, rather it is minus t plus t1. So why there is a mistake? You have like u of t. If it is u of t and if you shift in the right hand side direction, then it should be minus u of t minus t1. Okay. Left shift u of t plus t1, something like that. But remember that shifting you have performed not on ut, rather on u of minus t. Since the shifting was performed on u of minus t, reflected signal, traditional definition, traditional notation of positive shifting by minus and negative shifting by plus gets reversed. So this is a positive shifting, right hand side shifting, positive shifting with respect to u of minus t. So positive shifting with respect to u of minus t. So positive shifting means plus u of minus t plus t. Can you get the point? Or this can also be done from, or this can also be t only. So what you have done, you have first reflected the signal, then shifted. Right? Else what you can do, so first you shift the signal, first you shift the signal, delay, and then you take the reflection. So what you can do, if you delay the signal first, okay, let me go to the next slide.
Directly we can do non-conventional.
Advance, yeah, that is also, but then the shape will be different. It's also a non-causal thing. Okay, let me just give you the example. Let me continue with this one. You have already got this one, na? U of t. This is u of t as a function of t. This is 1, this is 0. Okay. So last time what you have done, first reflection, then shifting. So now this is causal, as you know. This is a causal signal. Now first you go for shifting, right? And positive shifting delay. How does it look like? Make it like this. 1 at t is equal to t1. What is that? Delay. So what is that? U of t minus t1, right? This is minus. This is not plus, right? Because you have performed this on u of t. Okay? Shifting first. And then you reflect. Now if you reflect, what do you get? First you have to reflect the signal. Okay? And then if you reflect this, what will you get? You have to reflect the signal with respect to what?
Y-axis means
T is equal to 0. So there could have been two different types of signal. So I can call this signal this is also causal, right? This is causal. What about this signal? What about this signal? Is it anti this signal? This signal? Non-causal, right? This is 1, this is say T1. What about this signal? Is it only non-causal? Last signal? Yeah, it is non-causal. True, it is non-causal. And apart from that, it is also anti-causal. Yeah, it's non-causal because it doesn't obey a causality property. At the same time, it is also because, as you know, that all non-causal signals are not anti-causal, but all anti-causal signals they are non-causal. Okay. So that is all about the causality and discussed about the causality property. And most of the cases, as I've already told you, that the causal signal and the causal system. Okay. Practically. So after that, now let's move to this is property number 5. That is an invertible system. Suppose you have, let's call it S. We have provided x of t, and we have got the output y of t. That particular system is said to be an invertible system if you can produce another system, if you can design another system S inverse, if you can generate another system S inverse, and if you feed this one y of t, you will be getting t back. Is that one clear? A system is said to be an invertible system. Not all the systems are invertible. There are some systems which are invertible. Your input is x of t, output is y of t. Now suppose I would like to generate the output. I would like to output from the output itself. So that output of the first t, suppose it is possible for you to generate, or it is possible for you to design one system as inverse, S I N V, which can produce x of t out of y of t. But properly, and this is true for all x of t. Yeah. So you have got some system x for which your input is x t, output is y of t. Okay. Now suppose I would like, so y is your output. Now suppose I would like to perform the reverse operation by means of a system which can give me x of t when wave is excited with y of t. Now had this been the case, and if this is true for all x t y t combination, for all input combination, because the signal property is based on, as I told you last year, signal property is based on for all possible independent variables. System property is based on for all possible signals. Now, if this condition holds good for all inputs, then I can call, okay, the system is an invertible system. And properly you have to get that particular x from where you have obtained y of t. Okay. Now, there are some systems, there could have been some system for which this one-to-one mapping is absent. It is possible. You know, system is a mapping from signal to signal. So just like now there could have been one-to-one mapping. You have studied functions in your class 11, class 12, right? Mathematics. So since it's a mapping, so it could have been one-to-one mapping, or it could have been many-to-one mapping. If you have many-to-one mapping, so there are multiple x of t. I mean x1t, x2t, x3t, x4t. There could have multiple x of t for which your output is y. Okay. Now for this case, it is not possible for you to design a system S inverse which, upon receiving y of t as its input, can produce x because you don't know whether it is x1t, x2t, x3t or x4. Right. Example is say y of t is equal to x squared t. Let's consider, let us take the input output relationship for a system is given y of t is equal to x squared t. Okay. And now if I restrict, okay, xt is positive. Suppose I restrict. Suppose I restrict y of t is equal to x squared t and I restrict the condition that this is only defined for xt greater than 0. Xt greater than 0. Then the system is invertible. But you know, when I call it like for all possible input, then you cannot restrict something. Then you cannot restrict. So if your input is 5, output is 25. Input is 10, output is 100. Right? Input, so I have provided some restriction. Input cannot be negative. 1, 4, 5, 7, 9, fraction, anything, but cannot be negative. And according to you know what is my S inverse? Basically, square root of that. Output is basically square root of the input. But if I forget about that particular restriction, if I do not restrict the input to be strictly positive, if I call it okay y of t is equal to x squared t for all xt, then your system is not an invertible system. Because if your input is 5, output is 25. The input is minus 5, output is also 25. Now for the inverse system, if your input is 25, you don't know whether it is plus 5 or minus 5. So the system is not invertible. Because your input is 25, suppose for the invertible system, inverse system, input is 25 and output is equal to say minus 5. That means what? You have not produced the proper input. 25 minus 5. Can you get the point? 5 to 25 through square law and 25 to 5. So the system is not invertible. Here? Can you give me an example of an invertible system? Any invertible system? Example of an invertible system. This is not invertible. This is not.
X of minus 2.
Huh?
U of minus 2.
U of minus 2. No, you tell me X relationship. YTX. YTX relationship.
Yt equals to x of t plus 2.
Huh? Yeah. Yt is equal to x of t plus 2. Or x of t plus k. Yt is equal to x of t plus k. What will be the inverse system?
Minus for all.
Yt is for all xt. Yt is equal to xt plus k as mentioned. Some input is something like, some system is something like that. Y of t to x of t plus k. All xt for all k. That is the system itself. What will be that is for the system S. So for the inverse system, I like y of t is equal to x of t minus k. That is for S inverse. Okay. Let's call a system like y of t is equal to e to the power xt. Y of t is equal to e to the power xt. Let's y of t is equal to e to the power xt. Let's consider this system. So far we have discussed so many about the system itself. Let's call y of t is equal to e to the power x of t. And let us try to characterize the system. The system is defined like this: y of t is equal to e to the power x. Okay. Now let's start from the very first property. Doubt? Anybody having any doubt? Y of t is of t. Question number 1. Is the system memoryless? Is the system memoryless? Y of t depends on x only. So it's a memory, it doesn't depend on the previous values of x of t. Okay, so the system is memoryless. Second, is the system stable? Vivo stable? Is the system Vivo stable? Yes or no? How many in favor of first? How many in favor of yes? Question is whether the system is a Vivo stable system or not. How many in favor of no? But this time, democracy doesn't win. Because the Vivo stable system. Why? What was the definition of Vivo stable? What was the definition? So if the input is bounded, output is also bounded. So some of you have mentioned that this is not Vivo unstable system. Why? Input means what? Input is bounded. That means what? This x of t or mod of x of t is less than equal to mx for all x. I mean for all t, right? So mx is a finite quantity, and that mx has to be less than infinity, right? So this is less than infinity for all t. So therefore, what about this y of t or mod of y of t? This is less than or equal to what? E to the power mx. Is it less than infinity? Yes, as long as mx is less than infinity, mx is also less than infinity for all t. So as long as the input is bounded, output is also bounded. So system is Vivo stable. Bounded input, bounded output stable system. What is the third property? What was the third property? Can you remember? Time invariant. Yeah. Is it a time invariant system? Yes. Invariant system. It's time invariant. Time invariant or shift invariant. Number the causal system. Non-causal. Why?
E power of minus 1 of the mod.
Is it a causal system? My question is it a causal system? Don't get confused with the causal signal and the causal system. What is meant by causal signal? The causal signal is something for which the signal value is less than 0, signal value equal to 0. That is a causal signal. What about the causal system? The causal system obeys the cause and effect relationship. That means the output appears only after the input, or right at the time when the input is. If xt starts from t is equal to t naught, yt also starts from t is equal to t naught. It's a causal system. We will talk about causality more in detail. First, last one. Is the system invertible? What is the invert system? System, okay. So, from this particular system description, y of t is equal to the power x of t, we can, these are the properties. Now, having said all these different properties, 5 different properties, like the memory, on the basis of memory, reverse stability, the time invariance, or space invariance, or rather shift invariance, the causality, and the inverse property. Now, let us move to the very fundamental and very useful property of a system with which we deal a lot. Right. And that particular property is having 2 different sub-properties. Okay. So the property as a whole is known as the linearity property. Linearity. Okay. And this linearity is having 2 different sub-properties. One is known as the additivity, second one is known as the homogeneity property. So let us now try to write it down. That's the most important one. The linearity property. Linearity. It is having 2 different sub-properties. One is the additivity, and second sub-property is the homogeneity. And if both of these 2 properties are satisfied by the system, that means additivity as well as homogeneity, then we call the system as a linear. The system can be additive, but not homogeneous. It is non-linear. System can be homogeneous, but not additive. Still non-linear. Neither additive nor homogeneous. Obviously, it is not linear. If the system is additive as well as homogeneous, then only. Can you get the point? So you have this B property, linearity. Okay? And then under this bigger property, under this umbrella, you have to additivity and homogeneity. If the system is both additive as well as homogeneous, then we call the system as a linear system. So, understand what is meant by the additivity of this system. What is that? So, a system, suppose this is your system for which your input is a, I call the set of inputs, okay, and I call it say x1 to t. Only 2 inputs are applied. x1t and x2t. I write something like this, x1 comma 2t. Means what? x1t is one input, x2t is another input, and the individual outputs are 1 to t. What does it mean? If the input is x1t, the output will be y1. If the input is x2t, output is y2t. If the input is x3t, output is y3t. Something like that. Okay. Now suppose system is an additive one. And if the input is summation t for I is equal to say 1 to n, say for example 1, 2, 3, 4, so 1, 2, 3, 4 up to n. And if the system is additive one, then the output should be summation I is equal to 1 to n yit. That means the sum of the individual outputs. Then the system is known as an additive system. Is it okay? Yeah. Input is x1t, output is y1t. Input is x2t, output is y2t. Input is the summation of x1t plus x2t. Is the output y1t plus y2t? Yes. If yes, then additive. If not, then let's have an example. Okay. So as he has mentioned, pretty popular input, something like popular system description. Say y of t. Say let's call it y of t is equal to. Let's call it okay kxt. Y of t is equal to simple amplifier. Y of t is equal to k times. Okay. Is the system additive or different? System? Yes. Okay. This is additive. Fine. Let's call y of t. So this is additive. No further explanation needed. Y of t is equal to x of t plus k. Y of t is equal to x of t plus k. The example that we have mentioned few minutes back. Y of t is equal to x of t plus k. System for input x1t, output is y1t. That is equal to x1t plus t. For the input x2t, output is y2t. That is equal to x2t plus t. Okay. So for input x1t, so I can call this y1t is x1t plus k. Okay. For all, so when I write this for all xt and for all, clear? What is y2t? x2t plus k, right? Now if your input is plus x2t, this is your system is input t plus x2t. What will be the output? T is equal to x1t plus x2t plus k, which is not equal to y1t y2t. So the system is not additive. Clear? So that okay, if k equal to 0, then the system is additive. If k system is additive. But remember that the definition holds good for all x and for all k. Suppose k is negative, k is positive, then the system additive problem doesn't hold. So when you properties for a system, then it has to be true for all. That for all is very important. So you understand now what is meant by the additive system. Okay. Now let's move to the second property, that is the homogeneity. What is that? Suppose you have a system for which input is x of t and output is y of t. Now, if the input is scaled by some constant, okay, some constant x of t, and if the output is also scaled by the same factor, for all such constants and for all such xt, for all constant and for all x, then we call the system as a homogeneous system. Can you get the point? a system is said to be a homogeneous system if for an input xt output is produced. Now I scale the input by some factor, by some constant c, and remember that c is any constant, can be real constant or imaginary constant as well, complex constant, any constant. And if the output is also scaled by the same factor, known to be homogeneous. Example for that homogeneous system. Okay, let's take the same y of t is equal to, we call it y of t is equal to k times x. Y of t is equal to k times x of t. Okay, if x of t gets multiplied with some constant, okay, then the output is basically the c times that particular input. So y of t is equal to k times x of t can be regarded as a homogeneous system. Now, as I mentioned that there are few systems which might be additive. For example, if you take that example, so let's consider this one, y of t is equal to k times x of t, as we have noticed previously. This system was additive as well as this system is also homogeneous. So this system is linear. Y of t is equal to k times x of t. What about this? Y of t is equal to x of t plus k. X of t plus k. Is it homogeneous? No. Isn't it? If your input is cxt, then the output is cxt plus k, and if you multiply yt with c, this will be cxt plus ck. So ck equal to k if c is equal to 1. This has to do for all c. Can you get the point? For input x of t, output should be x of t plus k. If the input is x of t multiplied with c, then the output should be what? Multiplied with c plus k. So cxt plus k. That is not exactly equal to c of y of t for all c. Okay, so this system is not homogeneous. So neither additive nor. So you find that okay, there are few systems are available which are additive but not homogeneous. In fact, most of the systems they are either both additive and homogeneous or neither additive nor homogeneous. For example, if you take this system, the first one, yt is equal to k of k times x of t, this system is additive, homogeneous. Second system, yt is equal to x of t plus k, this is neither additive nor homogeneous. Okay. Now, can you give me an example of a system which is additive, but not homogeneous? Any system which is additive but not homogeneous. A system which is additive but not homogeneous. Huh? Yt is it additive system? No. axt plus c is additive? No. It has to be additive, but not homogeneous. Very tricky. Additive but not. No, additive is not additive. Okay. I am giving the example of such a system. Let's consider the system y of t is equal to real part of x of t. Y of t is equal to real part because I have mentioned now for all xt it is true. Because system is additive now, so the system description can hold good for all the xt. It can be also a complex number. Okay. So y is equal to real part of xt. Let us take x of t is equal to say x of t. Let's take just two set of xt. One is x1t, that is say a1 plus jb1 t is equal to a2 plus jb2. Right? What will be y1t? What will be y1t? What is y1t? a1. So from here, what is y2t? a2. Okay. Now suppose my input is summation xit, where I is 0, 1 to 2, a1 plus a2 plus jb1 plus b2. What will be the output then? Yt plus a2, a1 plus a2 plus, that is equal to y1t plus y2t. What is the big deal? So you might think that okay, this is also homogeneous. This is additive, huh? Additive. You must take this additive system. Okay. So you might say, no, this is also homogeneous. You multiply 80 xt with just check. Multiply x with any constant and do the same thing, kxt, something like that. Are you convinced that system is non-homogeneous? How many of you are convinced that this system is non-homogeneous? Only 2, 4, 5. Why? Because I have told. Huh? Yeah. That's the proper answer. So when I say that multiplying with any constant c, so that is the beauty of abstraction. Don't get constant within the periphery of real numbers. So that multiplication can be any number, by means any number. It can be with any complex number also. It can be with square root of -1, that is j. Now if you multiply x of t and make it cxt, where c is equal to square root of -1. Okay. Then what will be your x1t then? What will be x1t? Or rather, I should write xt only because there you have only one here. Make it xt only. So what is that? X of how much? Minus b1 plus j times a1. Isn't it? Minus b1 plus j times a1. So what will be y of t then? Simply b1. Sorry, minus b1. Right? But that is not equal to c times a1. Right? C is square root of -1. Can you get the point? So this system is additive, but not homogeneous. Because there is one example, one counter example. When your constant c is equal to square root of minus 1 j, then the homogeneity property doesn't hold good. So this system is not a homogeneous system. Although it's a so the final conclusion is that this system is a non-linear system. Non-linear because additive but not non-linear. Okay. Now let's move to the second combination. The system is homogeneous but not additive. System is homogeneous. Okay. But not additive. Y of t is, how can I define y of t? System is homogeneous but not additive. Let me give you the example. Y of t is equal to, say, x of t multiplied minus 1 upon x of t minus 2, when x of t minus 2 is non-zero, and suppose this is 0 when x of t minus 2 is equal to 0. That is the system description. Y of t is equal to x of t into x of t minus 1. Okay, let's erase this part. Clear this. Let's make it black. Y of t is equal to x of t into x of t minus 1 upon x of t minus 2 for x of t minus 2 to be non-zero, and that is 0 when x of t minus 2 is equal to 0. Okay? So I have told that this system is a homogeneous system. You can check it. Let's multiply xt with some constant, any constant k. Okay. Multiply xt with any constant k. So what will be your output? So xt becomes xt becomes k times xt. So xt minus 1 becomes k times xt minus 1. xt minus 2 will become k times xt minus 2. Okay? So k times xt and xt1 upon k times xt2. So if k is non-zero, if what will be your output? K times this one, previous output. Satisfied? If k is equal to 0, 0 multiplied to something, this is also 0. Clear? So this system is a homogeneous system. Is the system additive? Just check. No, this system is non-additive. So this is an example. So this system is homogeneous, but non-additive. So final conclusion is that this system is non-linear. In fact, most of the systems that we deal with in practice, they are non-linear. Last day I given one example, a time invariance. Time variance. That okay, suppose your boss scolds you when you are in your job for the first day, in the first month. What will be your reaction? If the same thing happens after 2 months, after 4 months, after 6 months, then obviously your reaction is going to change. So human beings, they are typically their nature is time variant. They are time variant in nature. Right. Similarly, this linearity is a property which cannot be exhibited by the human, because when I call it that example is stability with respect to the reasonable person and unreasonable person. Yeah, I've given that example. So with respect to stability, you can always make a resemblance with the property of the human with the system property stability. But with respect to the linearity and with respect to time invariance, these properties cannot be associated with the behavior of the human being. For example, linearity means what? If you have xt, output is yt. If you have x1t, output is y. If you have input as x2t, output is y2t. Let's put together x1t plus x2t. Will you get x2, y1t plus y2t? No, typically not. I can give one familiar example. Suppose before your semester examination, you study for 3 hours for any subject X. You study for 3 hours, okay, and you get 60% marks in the exam by studying 3 hours, okay. Or say you get, let's say, 40% marks. You study for 3 hours and you get 40% marks. You study another 3 hours. You add 3 plus 3, 6 hours. Are you supposed to get 80%? No, 70%. Another 3 hours. 75. So it's basically that's basically non-linear. No matter how many hours you study, you can't get more than 100%. There is a saturation. And to get 100%, you have to study, say, 48 hours. Before the exam, not before the exam, totally. You will study for 2 hours, na? You will be getting 20%. You study for 2 hours for a particular subject in the semester. You study for 2 hours, you will be getting 20%. And another 2 might be 40%. Another 2 might be 60%. But if you add it 5 times, 10 hours, you get hardly 85%. If you study for 8 hours, you will be getting 80%. If you study 10 hours, you will be getting 85%. If you study for 12 hours, you will be getting 88%. And now the real challenges come. You have to get 95%, you have to study, say, 35, 8, 40 hours. It's a non-linear. It's a non-linear. Neither additive, no. You study for 2 hours, you will get 20%. Multiply 2 with 4, this side and that side, equation doesn't hold. Okay. So after discussing the properties of linearity and invariance, now we are at the very crucial juncture of this particular subject. And now, hopefully you have understood what is meant by signals, what is meant by systems, and what are the properties of signals, properties of systems and all. And now, right at this moment, we are at the very crucial juncture. Now, I've seen that there are few properties like linearity, causality, time variance, stability, and remember, all these properties are interdependent. One property doesn't depend on the other. They're independent to each other. You cannot find inconsistency between them. A system can be causal as well as stable or unstable. A system can be linear and causal, linear, non-causal, non-linear, causal, non-linear, stable, non-linear, unstable, causal, non-linear, stable, anti-causal. So there could have been lots of combinations and combinations, right? Out of that, we will pick up only one combination, which is very much for us to analyze the system. What is that? We pick up the property of linearity and we pick up the property of time invariance. And they together will give us a new property, a new class of system, which we call a linear invariant system. Or in short, we call it LI, or in general terms, LSI system. Linear time or linear shift invariance. LTI system in our case, where the signal is a function of time, and in general, this is an LSI system when the signal is not a function of time. In general. So there are so many properties. And remember that one property has nothing to do with the other. A system can be a causal, it cannot be stable. A system might be stable, but can be non-causal. A system can be linear, might not be time invariant. So there are different combinations. But out of different combinations, I would like to pick only one combination, that's the linearity on one hand and time invariance on the other. And these two together will give us one property which we call like a linear time. So if I add these two properties together, linearity and time invariance, linearity, that means within linearity these two properties are already embedded, additivity plus homogeneity, plus you add the time invariance property. Time invariance. These two together will give you linear time invariance property. Or in short, we call it LTI. Or in general, LSI, linear shift invariant property. Now you may wonder why I have picked that particular property. There are so many. Causality is also there, memoryless property is also there, invertible property is also there. But I have taken only these two, linearity on one hand and shift invariance on the other hand. Right. And remember that when I convert them together, this is called a linear time invariant system or linear shift invariant system. Now, in the next class, what we will do, we will basically study the property of this type of systems, LTI systems, and gradually we will understand why I have picked these two properties in particular, linearity on one hand and time invariance on the other hand, to analyze the system in a much more elegant way. Okay, not only in the time domain, but also in the frequency domain as well. Why? What is the specialty of this type of systems? Okay.